common symbol for it is phi of x, which is a function from Rn to R. A quadratic form is nothing but a generalization of a quadratic equation in one dimension to a quadratic equation in n dimensions. We call it a quadratic form. How do we define it? Okay. We have seen this in a previous class, right? Do I need to define what A, B and C are, or is it self-explanatory from here? It's self-explanatory, right? C has to be a scalar, B has to be vector, A has to be a matrix, right? Right now I am not making any special qualification on A. A can be any square matrix, right? So this thing. Now this is your first opportunity to put your knowledge of gradients into practice, right? So the claim is that and this is something that we will use throughout the course. The gradient of this expression is given by A transpose A times x plus B. Okay, those of you who have done machine learning would be very familiar with this, but we are not going to assume that. Let's prove it. Okay. So this is one proof which everyone should become very, very comfortable and familiar with, because as I mentioned, we will use it throughout the semester. Okay. So let's start, as always, start with the cycle first, then go to the car, right? We won't start from the left hand side of the expression, we'll start from the right hand side, rightmost term, right? When the gradient operator hits C, what happens? The constant, get rid of it, right? So the next term that we need to look at is B transpose x. And keep in mind the basic definition of grad f. Grad f is df by dx1, df by dx2. That, so just keep that picture in mind, okay? D by dx1, d by dx2. Okay, so now let's try to find out what is the gradient of this guy. So how would we work it out? So when in doubt, expand. So B transpose x, can I expand it in terms of the individual components, right? What would that be? Summation of Bi xi. Okay, actually let me make that Bj. All right. Now when I want to take the gradient of this, I need to find out d by dxi, right? That is the vector of this expression. So when I take the derivative with respect to xi, does anything survive? Which term? Only bi, everything else goes to 0. So this is going to be equal to bi over here. So if I now do this over all I going from 1 to n, what will I get? I'll get the entire, I'm going to get b1, whatever, bi and b. In fact, nothing but b, right? It doesn't get easier than this. I took a summation, I took derivative with respect to each variable, I'm left with b. So the first part is over here. This is fine, right? Now the second, any difficulty here? Quite straightforward, right? Okay. Now we need to look at x transpose ax. Okay. So let's just build some intuition. When you did simple one-dimensional calculus, when you encountered something like f into g and you wanted to do d by dx of this, what did you do? Product rule, you could say, right? So you would do f dash g plus f g dash, right? That was our product rule. Now what do we have? X transpose ax. It again looks like a product rule, right? Product of two functions. However, we have not yet written the generalization of product rule. So let's do that, and then this will be a piece of cake. Okay. There is one grungy way of doing it. What is that grungy way of doing it? Before we go into product rule, if you didn't know product rule, what would you do? Expand this big thing, right? You would write the matrix A multiplied by X. You will get n rows with this thing. Then you will multiply X transpose with it, right? And then you will take the derivative. It will get you the correct answer, obviously. It will just take a little bit more time. Now, we could do it that way, but I want to show you the product rule because later on in the course, you may have places where you have multiple times products of functions happening. So, if we know product rule, we can quickly solve it without this messy kind of math, okay. So, let's take an aside the product rule, okay. So, I am going to write f of x. Now, this time the thing to be careful about when we generalize the product rule is, in scalars it didn't matter how I wrote it. I wrote f into g or g into f, it didn't matter. Now, I have to take care of which guy is a transpose and which is a row vector, which is a column vector. So, I am going to write f of x as g transpose times h of x, okay, and obviously g and h, they are all n-dimensional vectors, okay. To make it clear, let me say n cross 1. So, these are n-dimensional vectors. Now, let us in particular look at g, right. So, g is going to be, remember g is a n-dimensional vector. So, g is going to be g1 of x, g2 of x, so on up to gn of x. This is the meaning of g, right. Now, when I say grad g, I have a function. Now, x is not a scalar, x is also a vector, obviously. I mean, that is what we are dealing with. So, what type of object is grad g? It is a Jacobian actually now. Why? Because it is a this g you can think of as Rn to Rn, right? Takes xn as x as input, which is n-dimensional, gives n-dimensional g out, g1 to gn. So, when I ask you what is grad g, it should be a matrix which is the Jacobian, right? And we already know what this looks like, right? Every row of this matrix is partial derivative of that component, right? So, if I write it as row, I mean this is just writing it again, dgi, actually let us, right? Each row is grad gi. So, grad g1, grad g2, all the way up to grad gn. I am just writing out the definition of Jacobian which we saw a short while ago, okay. So far so good. Now, what am I doing? I am multiplying g transpose and h, and I want to calculate, the whole point of the product rule is calculate this grad f for me, okay. Now, grad f is Rn to what? R. F is a scalar function, right. So, grad f is going to be a column vector, df by dx1, df by dx2 up to dxn, okay. So, if I want to find out grad f, the thing I should find out is df by dxi. If I can get this, I am done. So, let us write this out over here. So, df by dxi, right. I am just going to look at the definition of f. So, it is g transpose multiplied by h, right. So, this is going to be a summation gj of x multiplied by what? Hj of x. I am just writing out using this and this, that is all I have done. I have n components of g in a row vector, I have n components of h in a row vector, they are multiplied into each other and we have a scalar, right, and I am taking partial derivative with respect to xi, okay. Now, here is where we can start applying our, I mean we are building up our product rule over here. So let's apply product rule over here. Can I apply like a scalar product rule over here? Is Gj of x? It's a scalar, it's a function. Right? So let's start applying it over here. Okay. What does this remind you of? Del Gj by del xi. I is constant. What is the variable that is roaming around? J, right? So if I'm changing different j's over here, is there a, can you think of a compact thing that this thing under the curly brackets is hiding over there? Gradient g is there, but something a little bit more specific. Is it the jth row? Remember, what is constant over here is I. So let's look back once again at the definition of Jacobian. If I keep xi constant, am I talking about a row or a column? I'm talking about a column, right? So this is in fact including the summation. This is basically the ith column of G, which is getting multiplied by the entire H vector. Similarly, if I look at this guy, this is going to give me what? Ith column of H, of grad H. I should not say G, grad G. Ith column of grad, which is also going to be a matrix. Okay. Having seen this, you can see that this is going to be, so let's write it a little bit nicely. H transpose grad G's ith column plus this is going to be G transpose grad H, which is a matrix, but I'm only going to take the ith column. So just visualize the ith column of grad G is going to be this dgj by dxi. So column vector. I am multiplying it by H transpose. If I multiply it by H transpose, I will get exactly the summation. Similarly for the second term, right? And this is what? df by dxi. So if I wanted to now write like this, supposing I write like this. Just for fun, I am going to write them as a row vector. If I want to write it as a row vector, what will it look like? Just looking at it should give you an answer. These are all like columns, right? Right? So what is changing in each column? Only this I variable is changing. H transpose is remaining constant everywhere. So I can write this as H transpose multiplied by grad G, right? As simple as that, grad G plus G transpose grad H. Okay, and this in my notation is grad F transpose, because I defined grad F to be a column vector. So this is going to be grad F transpose, right? So you see, there is nothing grungy over here. It's just elegantly identifying what is in the summation and grouping the terms together. And then the final step is very simple. I just take transpose on each side. A transpose transpose is, if I repeat the transpose operation twice, I get back the same thing, right? So grad F then would be also, what is A B transpose? B transpose A transpose, right? So this is going to give me grad G transpose H plus grad H transpose G. So this is my product rule. Right. So let's just review this once. What did we do? We started with a hypothetical case where I was multiplying. I was making some function f by multiplying two n-dimensional multivariable functions g and h. And when I multiplied them to find out their gradient, I looked at df by dxi, applied the scalar product rule to each term, identified that it looks like a summation, and that summation was basically the ith columns of each of the Hessians, I mean Jacobians, and we get a product rule. Okay. So what is the term that we are looking at now? We wanted to find, coming back over here, grad of x transpose Ax. This is what I wanted to find out. Okay. And let's just remind ourselves what was f was G transpose H. That was what the product rule was. Okay. So if what can we very simply do? I need to just identify this as something transpose multiplied by something. So the easiest thing is this can, for example, be my G, this can be my H. Now if I write it like this, you have the formula there in front of you. The first thing that I need to write is grad of G transpose, which is grad of X transpose. Let's just write it out blindly. And grad of H transpose, so grad of Ax transpose multiplied by G, which is simply X. Is this fine? I have just blindly substituted F and G where necessary, right? Is there any mistake here? I can make mistakes of transpose, so please correct me. Right, I had grad G, all right, that's fine. Okay. So what is, let's start from the left. What is grad X? It's an identity. And is it a vector or a matrix? It's a matrix actually, right? Because it's a function with n variable, n outputs, so to speak, x1, x2, and it's actually right. You can also just take the definition of Jacobian and you will see that you will get a identity, one on each column, right? This is perhaps the simplest derivative that you could take. So this will become identity. Ax remains Ax. Now what about grad Ax transpose? Let's just talk about grad Ax. What is grad Ax? Right. So Ax, if I say and take grad over here, this is simply, it's going to give me A. So can you see why grad of Ax is going to be A? Correct. So this is basically, if you open up the matrix, multiply it by x1 up to xn. If I take the ith row of Ax, if I take Ax, the ith component over here, what is that going to be? Summation of A ij xj. Summation is over j. Now if I take the derivative, what will survive? Only that one term will survive, which is going to be Aij. So like this, I get back the entire A matrix itself. So grad of Ax is going to be A. So putting this together, what do I get? This is identity. I get Ax plus A, there's a transpose sitting there, X. Right. So finally we get that grad of phi of X is A plus A transpose X plus B. Right. So pretty straightforward. No rabbits out of the hat. We just took everything from first principles. You know, a class 12 student could follow this derivation. There's nothing fancy over here, right? So just keep check of whether it's a column vector or a row vector and keep the indices in check. Okay. All right. So we are drawing towards the end of the review of calculus. We have just a few more concepts to revise and then we can be on our way. Okay. So we looked at the generalization of derivative.